So we get our test statistics from our observations, which is our sample statistics. And our test statistic tells us in terms of a standard deviation, how far is the observation from the null hypothesis? So we're asking the question, if the null hypothesis is true, how likely is it for us to observe the sample? Now, if the sample we observe is too unlikely, meaning if the test statistic is too far away from the center, from the mu, then we will reject the null hypothesis. So the question is, well, how far is too far? Right? Now, that all depends on how much risk that we are willing to accept that we are wrong. So remember, going back to the first page, remember that alpha represents type 1 error. So a type 1 error is if we rejected a true hypothesis. Right? Now, no matter how unlikely something might be, it could still be there's still a small possibility that it is true. But we have to be in a hypothesis test. Right, we have to be willing. We have to be willing to take that risk, and that's what alpha is. So alpha is a level that we choose. Right, as the person conducting the test. Right, we choose alpha, and that is and so if if the likelihood of our observation, right, is going to be less than alpha, then we are willing to accept that and reject the hypothesis. Okay, now alpha is going to determine our critical value. Now, how does alpha determine critical value? Well, that depends on the type of hypothesis test. So we have two types. We have a two-tailed test, which is illustrated here by the equal sign, and then we have a one-tailed test, which is in the inequality. Okay, so first let's talk about the two-tailed test. Right? And this is going to be very similar to when you look for critical value for interval estimation. Okay, it actually, in fact, exactly like interval estimation, or so when you do a confidence interval. So what we do is we take alpha, and if it's a two-tailed test, meaning if the hypothesis is an equality, we split that into two. So we take the alpha, and we take alpha divided by 2 on both sides here, and you will proceed. And so you will proceed and find the critical value here, and that critical value is what you decide, how you use to decide. Right? If your test statistic falls here outside, right, then we call this the rejection region. Right? This is the reject and reject. So if your test statistic is greater than this critical value, or if it's less than this critical value, then we will reject the null hypothesis. Right? We can write it like this: if the test statistic, and let's put an absolute value around it, if that is greater than your critical value, right, then we will reject. Okay. Now, if it's then the other way around, if the test statistic it is less than the critical value, then we will accept. I put it as write the absolute value just more of a compact way. The absolute value, remember, just means distance. So really, if you're not comfortable with the absolute value, just look at the graph, right, and then just see that if the test statistic falls within here, you're in the acceptance region. If it falls outside here, then you're in the rejection region. Right? And that's how we'll know if our observation is too far away. Right? If it's too far away here. And why is this a two-tailed test? Well, if the hypothesis is that it equals like 3,500, then I will reject this. I will reject the null hypothesis if I observe something really small, or if I observe something really, really large. Okay, now let's carry that over to a one-tailed test, the idea here. Now, in a one-tailed test, then where should my rejection region be? Well, let's take a look here. So if my hypothesis is that mu is less than 3,500, right, then if I get a really small number, then that's perfectly fine, right? Again, mu is here. This is 3,500. Right? If I get a really small number, it doesn't contradict my null hypothesis, so I'm not going to reject. However, if I get a really high number, then I will reject. And so then that's why our rejection region is going to be here to the right when our null hypothesis is less than or equal to. Okay, and then so instead of splitting alpha, the area, in half, we will put all of alpha here, and that will be our critical value. Right? So if your if your test statistic falls here, we will reject. Right? If your test statistic falls here, we will accept. Right? So everything to the left of the critical value is the acceptance region. Now, what about for this? All right, the idea is similar. Okay, so our rejection region then is going to be on the left because, right, this hypothesis is saying that the mu is a large number. Mu is bigger than 3,500. Well, then if I observe something that is really small, then I will reject this. If I observe something big, then I will not reject this null hypothesis, right? Because that's what it doesn't contradict what this is saying. But if I see something really small, then it will contradict what the hypothesis is saying. So my rejection region is over here, right? And I put all of the alpha here on this side. So again, that's my critical value that I find. If my test statistic falls here, that's the rejection region. And then if it falls within to the right, then it's the acceptance region. Okay, so let's do some example about critical value here. Now, critical value is going to depend on the distribution of the sampling distribution, meaning the critical value, just like with a confidence interval, will depend on the sampling distribution. So then all that means is if sigma is known, right? Then we use a z critical value. If sigma is unknown, then we use t distribution as an approximation to normal. Okay, so we use t distribution, and we need to include the degree of freedom as well. Right? And of course, in either of these cases, right? Remember from previous chapter, we still need to or still need a normality. Right, we still need to be able to establish that the sample mean has a normal distribution. Okay, so again, that we either assume that the original population is normal, or we use the central limit theorem. So we'll need a sample size that's large enough. Okay, all right. So here we go. Let's try this example. Right, we'll determine the critical value of the test statistic for each of the following large sample tests. Now, when that's the key word, large sample. That means my n is greater than 30. Okay, we just take that as assumption. Whenever the problem says large sample, we have a large enough sample size. Okay, and the sigma is known. Good. So we have sigma here. So then now that means we use the z distribution. We use z. We have normality. We can proceed with the test. Okay. So first couple of times we do it. Let's go ahead and sketch this out. We know that we're doing a left tail test. Alpha equals 0.1. Okay. So my critical value is there, and my alpha equals 0.001. Okay, so then I'm going to go ahead and use my app to figure out what that critical value is. By the way, whenever we look for critical value, we always write z of alpha half. It's just customary, even though clearly we are not dividing alpha by half here, because we're putting all of the area alpha into all of one tail. We still write z of alpha half. So that's just because all of the textbook is going to use that symbol. Okay. All right. So to figure that out, we know that we're using the normal distribution because we know sigma, and so let's go ahead and type in here. So make sure that's 0 and that's 1 because we're dealing with a standard normal distribution, and then we go ahead and put in the area. We can put it in the left here, and here we go, and that's it. So that will give us our critical value. Okay, so my z critical value is going to be negative 2.326. Okay, all right. Let's go ahead and here you can pause the video. Go ahead and try the next two. Okay, so right tail test again. Put all the alpha here. Use the amplify. That's what you should get. Two-tailed test, we will split alpha in half. So each tail, the area in each rejection region will be 0.025. Okay, and so therefore that would be 1.96. Now, here, right, if your test statistic is larger than 1.96, you will reject. If your test statistic is smaller than negative 1.96, right, you will also reject. Okay, now here on this bottom one, let's read the question. Determine the critical value for each of the following. Small sample, so we do not have enough sample size. Okay, and then so population standard deviation is unknown, so we don't know sigma. Okay, so we know that we must use the t distribution. Okay, but what additional assumption is needed to proceed? Because we don't have a large enough sample, we need to make a strong assumption, which is that the population, right, is normally distributed. Okay, why? This is a strong assumption because we have no idea what the original population is. Most of the time we don't. But because our sample size is too small, if we don't make this assumption, then we cannot proceed because then we don't know the sampling distribution. Okay, now once we made that assumption, we know that we use t distribution. Let's proceed. Again, left tail test. Okay, same idea here. Nothing much to change, except for now that I need to calculate my degree of freedom. So my degree of freedom here equals n minus 1, so which equals 14. Okay, and that will be my t critical value. So I'm going to go into my app here. I'm going to switch over to t distribution. Okay, and then put in my degree of freedom there, 14. And then here I'm going to put in my area, 0.01. But instead, I'm going to put it less than and equal. There you go. So that's my critical value. Okay, so my t critical value equals negative 2. Here we go. 2.625. Okay, all right, let's continue. Go ahead and try the next two, okay, and check your answer when you're done. Okay, here we go. Alpha 0.1, degree of freedom is 19. So I'm still in t distribution. Change your degree of freedom here, okay, and then that here goes to 0.1. Now I want greater than. Although it doesn't matter, just make sure even if you put less than, you can still just put a negative in front of the flip the sign of the critical value. Here my critical value. Now it is 1.328. Okay, do this quickly. Here we go. Two-tailed test. All right, same thing. You divide it by. Now I'm gonna divide the alpha in half. Alpha half 0.025. Okay, my degree of freedom equals 7. A minus 1 equals 7. So I'm going to change this into 7. And then my area here, 0.025. Okay, 2.365. So that means my critical value is 2.365 right there. Okay, so that means my the negative side is negative 2.365. So those are my critical value. Again, rejection region on the outside, and if the test statistic is within that, then we will accept the null hypothesis.